Uh, next we have efficiency. Efficiency of crane or motor. Efficiency. Efficiency of crane or motor. You will say a word output or input. Whatever we apply input, our input. So what will we get as a output? Okay, output. So input, I think both will be different. Try to understand over here. So efficiency of a crane or motor. So efficiency we will be presented by in by in. Okay. So remember, efficiency of a crane or motor is the ratio of output power to input power. Output power upon input power is the ratio of efficiency. Okay. So n will be equal to this, n will be equal to output power upon input power. Just multiply this by 100. So you can say P naught upon Pi multiple 100. P naught P initial. Output power, P is a power, output power and input power multiple 100. This will give us efficiency. Okay, efficiency of something. Now next thing, N is also defined. This is also defined as the ratio of useful work done to the total energy speed. With how much speed motor will be providing water with how much speed? It will depend input. What is input? Or you can say velocity, with how much velocity. So here in this can be written as useful work or useful power upon actual power. Okay. So over here, actual power, which this is equal to W upon T. W upon T. T is a time and W is a work. So for gravitation, we have mgh upon T. mgh upon T. Okay. Now, if a pump lifts water from depth, from here to till here, if a pump over here, lifts water from this height, okay, from this height, and to deliver, and here water we will get how much? This is a input and output is this water which is coming with some velocity. So deliver at rate of dm upon dt. dm upon dt. This is a rate of providing this water with velocity v. Rate of dm with the velocity v. Then power delivered would be how much? This power delivered of water. So formula would be P is equal to dm upon dt. This is the rate. Okay, just multiply gh plus v square upon 2. This came from equation. Okay, upon time. If water lifts without velocity, velocity is 0. So our formula will become Pi will be equal to dm upon dt. This will become 0. So gh will be as it gh. Okay, gh. Over here velocity is 0. If a pump is providing water with velocity, then you will use this formula P naught P output. Now we have equilibrium. Equilibrium means net force. Just understand net force will be zero when it comes to equilibrium. Equilibrium. Equilibrium means net force is equal to zero. Equilibrium. F net is equal to zero. F net is equal to means net external force is equal to zero. If a body is at rest, body is in rest, body will be in rest. If a body is moving with velocity, constant velocity, body will be moving with the same velocity. Okay, that means there is a net external force which is zero. Net external force which is zero. So this is a definition of equilibrium. Okay, okay. So TWC means work done by conservative force. Work done by conservative force will be equal to D minus, not D minus, but minus du minus du minus du. Here U is the potential energy. Okay, potential energy. So you now dWc can be written as F into dx. For a small part, we have dx and minus du. F force by conservative will be equal to du upon dx. du upon dx. Try to visualize over here. The relation we have relation of ux. ux. Clear? ux. This is a curve. They want over here. So this will be slope. Angle is 45. So tan alpha will be dy upon dx. So y is u, d upon dx will be equal to 0. Slope over here is 0. Slope over here would be also 0. du upon dx will be 0. Over here du upon dx will be 0. So net external force is how much? 0 at this point. Clear? You know that slope can be written as tan theta. This can be written as tan theta will be equal to dx upon du upon dx, which is a slope. So f is nothing. This f is nothing. This is a minus slope. Clear? This is a minus slope. Types of equilibrium. We have seen definition of equilibrium through graph. Graph says that at the point where slope is tan theta, this is tan theta is equal to 0. dy upon dx is equal to 0. Okay. This was meaning of equilibrium. Now let's say types of equilibrium. Types of equilibrium. First we have stable equilibrium. Which is stable equilibrium. Stable means x and f are in opposite direction. F and x are in opposite direction. If you will displace the body slightly, it returns back to stable equilibrium. In just opposite, we saw that du by dx, so just opposite it would be dx upon du. dx upon du. Negative will be same. So y is a minimum, u is a minimum. So double depreciation of this du upon dx will be more. du dx square will be more than 0, will be more than 0. Try to understand. This is a circle. Look at over. This is a circle. There is a body. If we move this ball slightly, then what will happen? What will happen? Over here, potential energy. So to move, to bring over here, or you can say to bring over here this object. So what would be minimum potential energy? Minimum potential energy. Minimum potential energy. Just to bring this from here. This is what we have to find. Which is more. Okay. Potential energy. Now next we have unstable equilibrium. Unstable equilibrium. Unstable equilibrium. If we move the body slightly, it will move towards stable equilibrium position. This was over here. If you move over here till the over here, so what will happen? This will come again over here. This will come same position, at the same position. So means double depreciation of u upon dx square will be negative, So y will be, or you can say y will be minimum, maximum. Okay, maximum. Third which is a neutral. Neutral equilibrium. Neutral equilibrium. Neutral means neither more, neither less, only 0. P is a constant. Potential energy is a differentiation of du upon dx square will be equal to 0. Neutral means 0, unstable means potential energy is a maximum, and stable means potential energy is a minimum. Okay, potential energy is a minimum. Here you can say over here potential energy will be minimum. Not over here, but over here will be minimum. Height is something is a height, but when this object will be brought over here, then what will happen? Potential energy will be more. Yeah, so this will be known as unstable equilibrium, and this will be known as stable equilibrium, and this will be known as neutral equilibrium, where potential energy is 0. Now let's take question. Question is, I will read, not write. So the PE, which is the potential energy. Potential energy of a particle in a force field is how much? Potential energy is A upon R square minus B upon R. In a force field, where A and B are positive constant and R is the distance of a particle, or you can say radius, okay, radius of the center, from the center, distance of a particle from center of the field for a stable equilibrium, and the distance of a particle would be how much? Try to solve it. This is given, okay, and you will simplify this. This will be equal to A R square AR square minus BR reverse minus 1. Am I correct? Yeah. For equilibrium, du upon dr is equal to 0. I think equilibrium is neutral over here. Yeah, constant. Equilibrium over here is a constant. So value of u is given, which is how much? This much. So for equilibrium, neutral, just put value. So this AR square minus BR raised to power minus 1 dr, which is equal to 0. Okay. So depreciation of AR square will be how much? A minus 2 R. Remember, this is minus 2. Minus 2, we will bring this minus 2 downward, and minus 2 minus 1 will be minus 3. Okay, minus 3. Then we have minus this minus minus 1 and minus 1 minus 1 minus 2. Okay, minus 2, which is equal to 0. Am I correct? So minus 2 AR raised to power minus 3 plus minus plus BR raised to power minus 2, which is equal to 0. Try to understand. So this can be written as minus AR, not AR, minus 2A upon R raised to power 3 plus BR, not PR, but B upon R raised to power 2, which is equal to 0. Which is equal to 0. Yeah, 0. Look at over here. Here is a twist. Here is a twist. Here is a twist. Twist is just multiple R3 in both fraction R3. What will happen? Minus 2A upon R3 plus R3B upon R2. What will happen? This will cut complete, not completely, but one will live over here. This completely. So minus 2A plus BR. Just we multiplied both fraction by R raised to power 3, and we got a value of R. Okay, BR is equal to 2A, and R came as a 2A upon B. This is our final answer. Now your work is to see how did R come over here. Look at over here. Potential energy of a particle in a force field in a circle was given, which is A upon R raised to power 2 minus B upon R. This one. We just simplified. We removed the fraction. So this became AR raised to power minus 2 minus BR raised to power minus 1. We know that when power goes upward in numerator, then it becomes negative. If it is already negative, this will become positive. For equilibrium, for neutral, we know depreciation of du upon dx will be depreciation of d upon u upon r will be how much? 0. For neutral. Just we substituted value of u over here. We know A is a constant, B is also constant. Okay, A is a constant, B is also constant. So minus 2 will come downward. Minus 2 minus 1 minus 3 minus as it, B is a constant. Okay, R raised to power minus 1. So depreciation of R raised to power minus 1 will become minus 1 minus R upon r raised to power minus 2. Clear? So this minus 2a r raised to power 3, just we wrote this into, just we converted this into fraction form. It is fraction form, you can see. And then we multiplied r3 in both the fraction, so that this this can be removed. So finally we got minus 2a plus 2 plus br is equal to 0. From this equation we got value of r. Question was asking, I think question was asking radius. So the distance of a particle is how much? This is the distance, 2a upon b. 2a upon b. Clear? Now next question. Next question. The potential energy between two atoms in a molecule, and potential energy between two atoms is given by ux, which is a x square raised to power 12 minus b upon x raised to power 6, where a and b, try to understand, a and b are the positive constant, means du upon dx is a constant, okay, constant, and x is a distance, between atoms. The atoms is in stable equilibrium when x is stable equilibrium, when x is how much? Just put d upon dx as a 0. So value of this will become a raised to power x minus 12 minus b raised to power x raised to power minus 6 upon dx, which is equal to 0. Now look at over here. This is our a. Minus 12 a x raised to power minus 30, minus plus b minus 6, or you can say 6b x raised to power minus n, which is equal to 0. Finally we did differentiate it. Okay, till here this is correct. Just convert this into fraction form, then see, minus 12 a upon x raised to power 13 plus 6b upon x raised to power 7, which is equal to 0. Now your work is to look at over minus 12, or you can say 6b raised to power x 7, 12a upon x raised to power 13. What is happening over here? 6 to the 12. This will cut by x raised to power 6. It means we got the value of b is equal to 2a upon x raised to power 6. Am I correct? So value of b is this much, and value of a would be equal to bx raised to power 6 upon 2. This is value of a. So value of x will be how much? This is value of x. So 2a is equal to x6b. Am I correct? Over here 2a, b will come downward, b x raised to power 6. Clear? X can be written as 2a upon b of raised to power 6. This is our answer. Final answer is this much. Final answer would be that much. Now collision. Now collision. Collision, collision, collision. Collisions. Collisions. In collision, velocity of a body is affected by affected by others. You will see difference between velocity of a body before collision and after collision. This is what is a collision. Okay. So velocity of a body is affected is affected by is affected by others. Clear? Change of velocity after collision, before collision is our collision. After event, velocity of a body before event and after event is a collision. Okay. The any type of a collision, any type, elastic collision, inelastic collision, and any type of a collision. Even we will explore types of a collision. So in any type of a collision, momentum remains conserved throughout the collision. Momentum will be remain throughout collision. Okay, momentum will remain same. Head or one dimensional collision, not head on. First type of a collision, head on or one dimensional collision. One dimensional collision means object is moving on one dimension. The object is not moving between two dimensions. Okay, if object is moving in one dimension, in that case before and after collision body move along the same straight line. Remember, before and after collision you will see that object after collision, you will see object is also moving in straight line. This is what will happen. Reason is dimension is the same. Dimension is a one dimension. So after collision, you will see that both object is moving in same straight line. Okay, the same straight line. Oblique. Next we have oblique. oblique, oblique, or oblique or two dimensional collision. Here you will see body can go in any dimension, in two dimension, in two dimension. So do not move along same line. Here you will see that if two bodies in this from this side and from this side, two bodies are coming. Okay, two bodies. So you will not see that two bodies are after collision, two bodies. These two bodies will be moving in same in one straight line. No, this will. It is impossible. Yeah, it is impossible when we have a two dimension. Yeah, when we have two dimensions. In that case, bodies can go anywhere in x-axis, and in y-axis, Okay, so here we can say two bodies will not move only in a straight line after collision and before after collision. After collision. Remember, oblique means two dimension. Head-on means one dimension collision. One dimension collision. On the basis of loss in kinetic energy. Yeah, we will see loss of a kinetic energy after collision. So therefore, there are mainly two types of a collision. On the basis of a loss in kinetic energy. Loss in kinetic energy. On this basis, we have two types of collision. Two types of collision. First we have elastic collision. Elastic collision. Try to understand. Here, when you are taking elastic collision, you will see loss of kinetic energy. Yeah. Of course, after a collision, yeah, there will be almost there is some kinetic energy will be lost by the body after collision. Yeah, it is a possible. It is a possible. So this is first elastic collision. Okay. So let's explore it in details. What is the meaning of elastic collision? Let's say there are two objects. This one, mass is m1, and velocity is u1. The another object, m2, like that they are moving, and velocity is u2. Okay, u2. At us u2. After some time, the m1 moved with more velocity, and m2 with a less velocity. What will happen? Both will stick like this, m1, m2. This is what will happen. This will happen when velocity of m1 will be more and velocity m2 will be less. Then both will stick to each other. Now what will happen? Both will move. In this case, now both objects will move with the same velocity because both are stick. Both are together. Okay. So this is known as a deformation. Where both velocity after collision they are stick will move with the same velocity. Okay. Deformation completely over. Perfectly elastic collision. Here, if a body is stick together, then both will move with the same velocity. But here, what is happening? Over here? They are not stick. Okay, they are not together. Here, collision will happen. After collision, what will happen? This m1 will move another velocity, and m2 will move something else velocity. Means velocity will change. It changed after collision. Okay, this happens. This velocity can be more, can be less. I think it should be less than before. This is known as elastic collision. Try to understand. When two bodies are coming with some velocity, if after collision velocity are something else, then before will be our elastic collision. Okay, bodies are going there happened what collision. After collision velocity, this two bodies changed velocity according to earth, I would say, according to earth. This will be known as momentum of a system remains conserved throughout collision. Momentum, not kinetic energy. Momentum of a system. Momentum of a system conserved throughout the elastic collision. Momentum will be same, means P is equal to mb. You can see over here we are getting P is equal to mb. After collision we are getting P is equal to mb. Same, but kinetic energy is lost after collision. Kinetic energy will be something else, lost. Okay, not conserved throughout the kinetic energy initial. You can't say that kinetic energy initial will be equal to kinetic energy final. No, some no, they would not be conserved. Clear? So for this we have mb plus m2 v2 is equal to m1 v1 plus m2 v2 v2. This is a before collision and this part is a after collision. Clear? Before collision, after collision, I hope you have understood. For this kinetic energy we know is nothing but 1 by 2 m1 v1 square plus 1 by 2 m2 v2 square. This part is before collision. Okay, 1 by 2 m1 v1 square plus 1 by 2 m2 v2 square. This is the after collision. This part is before collision, this part is after collision. Okay, I hope you are understanding. So let it be equation number 1. Let it be equation number 1 and let it be equation number 2. Add it over there. Add them together. If a mass of two bodies are same, try to understand. Next point. This m1 and m2. Next condition is if v both are moving with same velocity. If a mass of the two bodies are same, identical mass, then velocity is exchanged. Hence v1 will be equal to v2. Okay, v1 will be equal to u2. v2 will be equal to u2. Means if velocity is the same for both bodies, then then velocity will be exchanged after collision. Okay, after collision you will see that velocity is the same but will be exchanged. Look at over here. A relative velocity, just not take a velocity as a relative velocity. A relative velocity before collision is nothing but u1 plus v1 is equal to u2 plus or you can say v2 plus u2. From here we are getting u1 minus u2 which is equal to v2 minus v1. v2 minus v1. Remember, this is our relative velocity before collision. Relative velocity before collision. Okay, and this is a relative velocity after collision. After collision, velocity is relative over here, or velocity of approach, velocity of separation, or you can say this is our velocity of approach, and velocity of separation, velocity of separation, v2 minus v1, u1 minus u2, v2 minus v1. Now look at over here. As we know, v2 will be equal to, from here v2 will be equal to u1 minus u2, but minus this positive, just this will become minus, so positive v1 from this equation. Putting these values of v2 in equation 1. We will get v is equal to m1 minus m2 upon m1 plus m2. u1 plus 2m2 upon m1 plus m2. u2. Now look at over here. I am going to draw a figure. This is object M1 is going with VU1 velocity in this direction. M2 is over here. M2. So after collision, over here, after collision, in this direction, y2. This is going in this direction and this was going upward. It was going horizontally, this M2 was going vertically. After collision, what will happen? This M1 will go over here, M1, and M2 will go downward. M2 will go downward. M1 and M2 will go downward by making an angle with the horizontal theta 1 and theta 2. Okay, with velocity in this direction v2, and this will be our horizontal direction v2 cos theta. This is one component of a v2 cos theta. Clear? this will be going like this with velocity v1 u1 u1 and with component u1 sin theta, I think so. u1 sin theta, one component upward would be u1 sin theta, and in this direction u1 cos theta according to this theta cos theta. Clear? What are you understanding? What are you understanding? You are understanding there was two objects. Okay, there was two objects. One was going horizontally, second was going vertically. At this time both came near to each other. After collision, what will happen? This went in this direction and second m2 went in this direction. It means both went into two dimension. So one would be in this direction, which will be our v2 sin theta. Okay, so just we broke the component of a v2 and the component of a v1. You can say according to theta, this was theta, this was theta. Just we broke over here. We broke the component so that we can find in which direction the bodies are going, in which direction after collision. Okay, that is how we will observe moving bodies after collision. After collision. After collision. So for x direction, horizontal, for x direction, pi is equal to pf. Pi is equal to pf means negative minus positive. Negative is equal to positive. Initial. This after final collision. After final collision. You are observing that after collision this m1 went in this direction. You can't say that m1 after collision went exactly horizontally, exactly vertically. No, you can't say. This after collision it is going in two dimension. Okay, so this with the u1 cos theta, with this much velocity, m1 is going horizontally. With how much? u1 cos theta, and with u1 sin theta velocity, it is going upward. This is what you are understanding. And what about m2? M2 is with the same m2. M2 is going with v2 cos theta in horizontal direction. Okay, v2 sin theta in vertical direction with the v2 sin theta. Okay, this v2 cos theta is our velocity. v2 sin theta is also velocity. Just we broke the component of the v2. Okay, we broke. Now next, for x direction, for only x direction, just to observe x direction. You know m1 u1 plus m2 u2, this m1 u1 m2 u1. Okay, it is equal to, this is equal to, just take horizontal component. I am saying horizontal component. So first we have m1, this is m1, so m1 into v1 cos theta. We are talking about momentum. Okay, momentum. m1 v1 cos theta plus m2 v2 cos theta. Just v2 horizontal component. This is our first equation. For y direction. Just take pi is equal to pf, which is equal to 0. Just take y component. So y component is u1 sin theta, u1 u2 sin theta. Okay. For this we have m1 v1 sin theta is equal to m2 v2 is equal to sin theta 2. Try to understand. This is the second equation. Look at it. Before collision, momentum was this much, and after collision, momentum is this much. For y direction, before collision and after collision, momentum is same. I think so. Same. For y direction. For y direction. What about kinetic energy? So kinetic energy will be equal. Kinetic energy initial will be equal to kinetic energy final. Okay, fine. 1 by 2 m1 v square plus 1 by 2 m2 u2 square, which is equal. Okay, this is third equation. We will use this three equation for solving numericals of elastic collision in two dimension. When elastic collision is in two dimension, then this three equations will be used. Okay, first equation was this equation, and second equation is this m1 u1 plus m2. Just add this momentum plus after momentum. Okay, horizontal, and then vertical. Vertical will be before collision equal to after collision. Okay, for y kinetic is initial kinetic is equal to final kinetic. There are three equations. Now in elastic collision, we have covered completely about elastic collision. Now it's a time to explore inelastic. Inelastic inelastic collision. Look at over it. After collision, both bodies stick together and move. Stick and move after collision. Okay. After collision, what will happen? After collision, will stick and move together with the same velocity. Velocity for both would be same. Clear? When it comes to momentum, so momentum remains conserved. Momentum will be conserved, means Pi will be equal to Pf. Okay, so kinetic energy initial will be more, but after collision, kinetic energy final will be less. Okay, because it will stick, that's why. So of course it will be less. No, some energy is lost. Some energy is lost due to collision. Let's visualize this m1 with u1 velocity, m2 with u2 velocity. After collision, both are sticked like this. Both are sticked, m1 and m2. So if after collision both are sticked and moving with the same velocity, this will be known as inelastic collision. After collision, velocity for both bodies will not be different, will not be separate. Okay, will not be separate. Combined deformation. So over here you can write m1 v m1 u1 plus m2 u2 plus m2 u2, which equal to after collision. So velocity is a constant for both body. Common I would say. M1 plus M2. Okay. Momentum for first body M1 into U1 add, and then momentum for second body M2 into U2. Next, after collision. This velocity is common for both. This is for both. So B M1 plus M2. This thing can be written. That condition, this is a common. Okay. Reason is both are strict. Both are strict. Coefficient of restitution. Coefficient of restitution. Coefficient of restitution. It is nothing but ratio of velocity before collision and ratio of velocity of bodies after collision. Relation between them is a coefficient of restitution. Coefficient of restitution. Try to understand. It is represented by as follows. Is the ratio of velocity of separation. To the velocity of approach. You can write this is equal to velocity of separation upon velocity of approach, which is equal to relative velocity before collision. This is a relative velocity before collision and upon relative velocity of after collision. Okay, it can be written as this is equal to v2 minus v1. Change in momentum, v2 minus v1 upon u1 minus u2. Okay. For perfectly elastic collision, E will be equal to 0, but for perfectly inelastic collision, E will be equal to 0. Okay, perfectly elastic collision, E will be equal to 1. Perfectly inelastic collision, over here E will be equal to 0. Value of E depends on material of a colliding body. What kind of material you are taking to collide? Okay, so every collision will be elastic and partially. Motion in a vertical. Next we have motion in a vertical circle. Motion in a vertical circle. We will take one dimension circular motion. One dimension circular motion. This is circular motion. Object is over here. When he reached at B point, at the C point, yeah, this M is the same. Vertical motion in a vertical circle. Here you will observe motion of a body which is moving along the circumference of the circle. So vertical like this vertical. Try to understand meaning of this figure. When this object will reach at B point, so minimum potential energy would be how much? Minimum potential energy to bring this mass of over here at B point. So what would be minimum potential energy? Okay, minimum potential energy. If a force is zero, remember if a force is zero, so work will be also zero. If a tension is zero, tension of force is zero. Okay. If x is zero, x means displacement. So work will be also zero. T and F both are same. Both are same.